start again.
Okay. Yeah, so I wanted before we start, just wanted to make a few comments. Last night I started worrying that when Michael started talking about let's start a project this week, that it may have set unreasonable expectations as to how quickly it's possible to learn Lean. I mean, there really is a very steep learning curve. So this semester I'm teaching undergraduates at Carnegie Mellon to formalize, and it's a 14-week course. And the first 7 weeks, we spent the first 7 weeks just working through mathematics and Lean and learning all the basics. And now, the hope and expectation is that they're at the point where they can sort of pick a project and start working on it. They've been doing homework every week and so on. We have done, if you go to the Lean community web pages, you can find all kinds of online meetings, many of them with video recordings. Things with names like Lean for the Curious Mathematician and so on, that are kind of designed to be crash courses in learning to use Lean. And many of those are a week long. But they tend to be pretty intensive. It gathers lecturers, and there are lectures, and there are exercise sessions, and there are TAs. And often with those, by the middle of the week, we'll try to get people working on projects. But it's a matter of choosing projects very carefully and having TAs working with people and helping them pretty intensively, and that would crowd out everything else. So we're not doing that. We're not moving at that pace. My goal with these tutorials is to really just kind of break the ice and just get you comfortable playing around with Lean. And there are really three motivations for that I'd like to share and discuss a little bit. So the first, that you might like it. It is formalization is still a pain in the neck. The amount of information you need to kind of absorb. I mean, it's hard to do it casually, right? You really have to invest a lot of time in learning it. But you might find that, hey, this is a lot of fun. And so I want to make sure that if you do feel like you have the time and the energy and the effort to really learn how to do it, that the hope is to get you started to the point where you can then spend time with the resources available and get as far with it as you want to go. Perhaps even as far as contributing to MathLib one day, or getting involved in some of these collaborative projects that are now springing up ever more frequently. But another reason that I think it's important to talk about is, I often try to make the case to mathematicians that even if you don't have time to really invest the time and energy to get comfortable with the technology, it's still important to be familiar with it, because your students are. I mean, these days we're seeing college students and even younger finding Lean online and starting to use it, and learning it, as they learn mathematics. And so I think in the years to come, you're going to see more and more young people that are kind of excited about formalization, and they tend to pick it up really quickly. It's for a certain generation, it's just kind of natural this kind of interaction is very natural. And I think, as mathematicians, we want to be able to support that. I try to make the case that mathematicians should be involved, because we want to make sure that they're still doing good mathematics, right? So they're going to be doing mathematics in different ways, but we still need to help guide them in developing as mathematicians. And the third thing is exactly related to the topic of this workshop, is that once you understand the technology, and what it can do and how it works, then you can better think about and understand how to build machine learning and automation on top of it. I have a PhD student, Josh Kloon, who's doing excellent work in automated reasoning right now. But his first project, when he started as a PhD student, was just to do a substantial and very interesting formalization project, which I can tell you about later if you want to hear about it. But the point is, even though he's working on automation, he's not doing formalization now. But you do a big formalization project and you kind of suffer through it, and you feel the pain of just kind of spelling everything out down to axiomatic primitives. And you think, God, we should be able to do better, right? So it's using the technology manually and just kind of hacking through proofs is not only important to understanding what needs to be built on top of it, but it's also really good motivation to get the automation going. So anyhow, what I propose to do is today do another kind of quick tour of Lean like I did yesterday, and go for about an hour and show you some more things. And at that point, I will have given you roughly a tour through the second and third chapters of mathematics and Lean. So the first one is just introduction, but the first chapter is just basics, things like rewrite and apply, which I showed you yesterday. And then the next chapter is logic, so how to deal with and or and quantifiers. And I wouldn't have shown you all of that stuff, but I would have shown you snippets of those two chapters. And then I propose, I'll stop and just, insofar as there's time today, we'll stick around. We can stay in this room right afterwards. But just do exercises, do things in mathematics and Lean, and I'll be on hand to answer questions. And really throughout the next few days, insofar as you have time to work on it, you can answer questions. And then I suggest tomorrow morning we start to look at MathLib and what's there, and try to formalize. I mean, right now we're doing the nuts and bolts, the low level interactions. But I propose that tomorrow we take a look at the library and try to formalize some statements. If you give me a heads up, I can try to pre-prepare. Now we can kind of muck around together. And that I'll say, let's not record that, because I'll be embarrassing myself with all the things I don't know. But yeah, if you give me a heads up, ahead of time, that I'd like to look at algebraic number theory, something about blah blah blah. I can sort of poke around MathLib tonight and try to figure out what's there. But that's also often a big challenge. Just to, even if you're really good at formalization, if you try to sort of do something in a new area, just to try to figure out what's in the library and how it works and how it's meant to be used is often.
I think that would be very helpful. So it's probably a topic in number theory is the most people who are doing it. So maybe at the end we can pick a subtopic and, as you say, okay, fun up with that.
Yeah, there's the I forgot his name, but there's a number theorist from BU, I think, who was working. Who actually asked me a question about it. Yeah, okay. And so I actually have one possible example. Okay, so before I start in, are there any thoughts or comments or questions? Okay, so let's do it. So I'd like to pick up. Actually, Melon, I really loved the question you asked yesterday. I want to pick up by responding more to that. So yesterday, I showed you rewrite, which is just equational reasoning. It's just, at some point with, high school students, we tell them there's this general principle that, equals can be substituted. I forget how, if A is equal to B, then you can replace A by B in any expression or something like that. And that's what rewrite does. It takes an equation and it just does the substitution. And then I also showed you the apply tactic, which is applying a theorem. You're trying to prove something, and apply is kind of a way of working backwards. You have a theorem that roughly the conclusion is what you want, and you say, okay, I'm going to apply that theorem, and now it reduces your task to then showing that the hypotheses of the theorem are satisfied. And so after giving you some examples of rewrite, I showed you an example. So this example is, of using apply, where you have theorems that say that to show that, A plus B is congruent to C plus D, it's a place to show that A is congruent to C and B is congruent to D. And Melanie said, oh, but these are equations modulo something. Why can't you just do the rewrite and the substitution? And so one way, I thought of one good way of explaining why you can't just use rewrite out of the box is just to point out that, so for example, if you modify the example to show that from the hypotheses that instead of showing this, suppose instead you just try to show that the absolute value of A1 is equal to the Oh, sorry, that's value. So the absolute value of A2. And let's see. Let's see, am I getting the absolute value bar? So let me just use abs. Right. So if we just change the problem slightly, that, just from the hypotheses show that the absolute value of A1 is congruent to the absolute value of abs A2 mod n. Of course, we won't be able to do it because it's not true, right? For example, -2 is congruent to 3 modulo 5, but 2 isn't congruent to 3 modulo 5. So it can't be just that, well, you have this congruence and you can substitute. You can only do substitutions in the context that respect the equivalence relation. And if you were new to mathematics as well as attractive theorem proving, you might think, well, gee, it would be great if there's some kind of mechanism where we can treat this equivalence relation as though it was an equality and do carry out rewrites and substitutions, but be guaranteed that we're only doing it in contexts in which you're allowed to do it, and we don't have to fantasize about it. I mean, this is what mathematics gives us, right? This is what a quotient construction is, right? If you quotient the set by the equivalence relation and you consider equivalence classes, then exactly what you're doing is you're converting the equivalence to an equality. But then you need to show that addition and multiplication on the integers kind of lift or descend to operations on the quotient structure, and we know that that's the case, right? So the quotient of the ring of integers is a ring, and then you're calculating in that ring. And what I really like about formalization is that it gives you a new way to kind of to understand what's going on with that process. And so what I want to do is sort of take you through. I want to do the theorem the way Melanie wanted it to be done, which is you're calculating of equalities. So let me show you how that works. So having played around with it last night, I came to learn that. So I think, where was it? Somewhere, yeah. I think if we add a natural number. So there is a notation, a construction for the ring of integers modulo m, but in the construction m has to be a natural number, right? So it's not set up to what are the integers modulo -5, and so it's and so the problem becomes a little bit easier. Instead of letting n be an integer, I'm going to change it to making it modulo a natural number. And let me do the trick of writing done. Okay, and you see that what it's done is it's insert a cast here. So this is the cast of natural numbers to integers. So
you're still saying A1 and A2 are
integers. I'm still doing it in the integers, but just the modulus. I'm saying even the modulus is an integer, but I'm saying it's an integer that's non-negative because it comes from a natural number.
But so now does this equality mean, or this equivalence mean equality in the ring Z mod?
No, so I haven't done anything. So this is the same problem. It's essentially the same problem, but it's slightly less general in that I'm requiring modulus. But it's really the same problem as it was.
But what was the casting then?
Oh, so the casting is that so the notation is A is congruent between modulo and integer.
Oh, it's just the casting because M was a nat.
And now M is just cast to a nat. Yeah. So the cast you're thinking of, we're going to get to in a second, right? So the point is now we want to rewrite this to an equivalence in the corresponding, to an equality in the corresponding ring. And happily, I tried this last night. We can ask Lean, well, what kind of rewrite rules? What can I? How can I rewrite this problem? And if you scroll down, and it's not one of the first things that comes to mind. But oh no, don't make a liar out of me. There it is. No. No way. That's crazy. Cast and only if. That is bizarre. Okay, well, let's do it manually. I'm looking for a theorem that says that equivalence modulo M is so you can prove an equivalence modulo M by proving the corresponding equality in the associated ring. Try it again just to see if moving things around. Did I miss it? Okay, well, let me just find it by. Oh no, it's this one. There it is. Okay, this is the one. It's this crazy Z mod int cast eq int cast if and only if. Well, let's just follow the instruction. Just do the rewrite and see what happens. So what it's done is it's converted the so the red tells you that this is about to change. It's converted the equivalence modulo statement to a statement about so there's an equality here. And then to figure out what the equality is, so this is an integer, 8 times b1 plus c1 is an integer, but now it's casting it to the integers modulo n. Okay. So what this rewrite says is that a is congruent to b modulo m if and only if when you cast a and b to the ring of integers modulo m, they're equal.
And so the only way to see where it's casting it to is to hover?
Yeah, so the fact that there is this up arrow there tells you that there is a cast going on. And I mean, what other information? I mean, if you kind of hover over this, oh, this is in Z. So if you hover over the full expression, yeah. So the full, if you just look at after the colon, it tells you that that expression is an expression in Z mod M. So it's interpreting that expression as something in integers modulo M. And then the arrow is the int cast. Okay. But then if you think what you want to do, so now you have this cast on the outside, but then what you want to do is you want to push the cast in, which reflects that the multiplication, the addition on the integers. So, right, respects the equivalence relation so that, you know, so casting and multiplying and adding is the same as, well, multiplying and adding and then casting after is the same as casting first and multiplying and adding. And let's just ask the simplifier to do it for us. It'll push the cast in. And there it is. You see that it did it, right? So now instead of casting A1 times B1 plus C1, it's casting A1, casting B1, casting C1, and then doing that.
Why did you put this like there before that as opposed to like after that as the next step?
Yeah, so what I'm doing is it's not the next step. I'm rewriting the step. I'm saying rather than just do a single rewrite with that, what I'm saying is use the simplifier and use the identity. So the if and only if. So the simplifier will use equations, but only if and only if statements to rewrite. And so I'm telling the simplifier, do that same rewrite and do all the other stuff you know how to do as well. That's what it's doing. And if you want to know what else it's doing on top of that, you can ask. And it tells you, if you look on the right where it says try this, it's using the equivalence we gave it. And the left arrow means it's using it backwards in the direction we want. And then you see there's this int cast add and int cast mul. So these are generic theorems. The cast is the generic cast. So you have a cast from the integers to any ring, right? And that's what the int cast is. And cast add and cast mul are generic theorems that work for casting any ring. And so the simplifier is using those. Okay. But now you have done this. Of course, we want to also do it for the hypotheses, right? So we want to have those as equations for corresponding ring. And so the easy way to do that is just tell the simplifier to not only simplify the goal, but do the hypotheses as well. Right? And now this is exactly, the argument that you have in mind. This is just rewrite. You just say, rewrite with HA and it replaced, A1 by A2 in the goal, and then use HB, and then it replaced, B1 by B2. And if you use HC, it's going to replace C1 by C2. And then after that, the two things were equal, and rewrite just applies reflexivity to finish it off. And so the error message is, you don't have to, done does nothing. Right? Yeah. Okay, so this is the proof that you had in mind. And it's not, well, it's not significantly shorter and easier than doing it, doing it with the apply. But it does have the virtue of, it really is, the first line says, change the representation, right? And then the second one is, then it's just a calculation. And this is, well, I mean, common in mathematics and common in formalization, that often the challenge is finding the right representation and then working with the representation, and things become easier. I think the other thing I wanted to mention with this example, oh yeah, so that's the one that doesn't work. Let me go back to the general statement where n is any integer, is that automation can also, well, should be able to get, the right automation certainly can get this. Even the simplest out of the box automation can do it in a couple of steps. If I ask, if I ask Lean to suggest things that I can apply, to prove this theorem, I mean, it says try int mod eq, it just gives me one thing to try. Don't worry about what refine and the question mark. It's saying basically apply int mod eq add, and I don't know what the second argument is, but for the third one, use hc. And if I if I ask it again, it comes back right away. It says, oh, I can finish that off with int mod equal. So just asking Lean, what it can apply, it finds things and applies it for you. Okay, and while we're on congruence, I'll just do one more example. But yeah, so before I do that, are there any questions? Okay, and again, I'm throwing all this, I haven't told you what simp is or the syntax for simp, and I'm just showing you examples. You can read about this all in mathematics and so I'm not expecting you to pick up the mechanics and all the syntax. I'm just showing you that it's there so that, when you see it in the book, it'll be familiar.
Can you just remind me, what is the rule as you move the cursor across the expression, what it's actually showing?
Yeah, so this is actually kind of nice. So this is Ed Ayers, who's a postdoc with me at Carnegie Mellon, implemented this. The kind of the red and the green tells you that right before, I mean, often, as you're stepping through the proof, things are changing, but things are, when there's a lot going on, it's hard to see what's changing. So the red means that, this is about to change. And then if you go to the end of the instruction, it tells you exactly the green are, those are the things that changed. But then as you step through, so I think simp applies all the rules all at once. So there's no, but rewrite is actually kind of cool. As you step through the things in the commas, like here, it's, it's just done HA, it's just done the rewrite, it's used HA. And so you see that, the A2 of it's just been changed. Then the next thing, HB, is going to change, B1 to B2. And so let's see, if we get there, we see that B1 is about to change. Then you go right after B1 just changed to B2. Yeah. Then C, yeah. Yeah. Oh, and were you asking about, how to interpret the context?
No, I was actually wondering, because I thought, this is great, because I thought you thought to write the rewrite as 3 separate lines. And
Yeah. So, yeah, I mean, formalization is painful, but the way to make it less painful is that there's lots of syntax and shortcuts and clever tricks. Again, they're power user things that as you've been doing it for a while, you learn, more and more tricks, but they're there to just kind of make things quicker and more efficient. So I guess just to do one more quick example that is also taken from mathematics and Lean. Let's just show that, let's just show that if A1 is congruent to A2, then for any natural number k, A1 to the k is congruent to A2 to the k. So that, in fact, and 1 to the k, congruent to A2 to the k. So this is certainly in mathlib, right? So if I say apply, Lean will tell me that it's just int mod equal k ha. But I want to imagine, suppose we were designing the library and we had the facts about addition and multiplication. We didn't have this yet. Let's think about how we would prove this basic fact. And so yeah, that's my question to you. So how would we prove this basic fact?
Induction.
By induction, yeah. So let's do induction and IH. And I mean, later I can tell you why induction prime and not, but this says do induction on K. And in the induction step, I want to use the same name K for the variable, and IH is going to be the name of the induction hypothesis. And we see two goals. And so the first one, that A1 to the 0 is congruent to A2 to the 0 modulo M. And so any thoughts about how to, so mathematically, they're both 1 and 1. And so, you might hope that maybe the simplifier can do it. And the simplifier, a little simplifier by, anything to the 0 to 1. And it knows that reflexivity, it'll try that. In fact, this is another one of those facts that just by unfolding definitions and contracting, Lean can do it. So it's as far as Lean is concerned, it's just the first case is really trivial.
When you type that there, does it know that it's only supposed to be doing that on the first goal?
Yes. Okay. So so there are 2 goals, and so now the next. So there's some tactics that will act on all the goals, but most tactics are designed to only focus on the first one.
I see, but some will do both. Okay.
Some will do
That's
all.
just a feature of the
yeah.
tactic. It just
And there are
works on
also
the first
commands.
goal.
You can also say apply this tactic to all the goals.
Okay.
There are meta tactics and so on. But yeah, so most tactics just address the first goal. And then it's considered to be good form. So when you actually put a dot, that actually it's called a focusing tactic. After the dot, there's only one goal. It basically brackets off all the other goals so that you're only, and you get an error message, within the dot if you haven't finished the first goal. And it's considered kind of good form to kind of write proofs in a structured way. This kind of shows that, if this was 6 lines of tactics, it shows that those 6 lines are just, solving the first goal.
Mhm.
And then the next dot, put another dot there, makes it clear that you're doing the second goal.
So when you go to the end of that line, that dot RFL line, it says no goals.
It says no goals, but it's no goals, not globally. If you open up all messages, it'll tell you that the proof, you still see no goals. Oh, there's all this stuff, demonstration stuff. Yeah, so it's not telling you that the whole proof is done. It's telling you just that within this focused subproof, you're done.
If you have like a long proof though, and maybe there are some dots or not, and we can of course see what happened here, but in a large text, is there some definitive way for you to know if?
Yeah, so you see that there's this kind of error message on the by, and there the error message is coming up saying you're not done.
Okay,
So
so you go to
yeah.
the by and see.
Yeah, and this is why often I like to put the word done at the very end. I don't know. It's very easy. I do this all the time. I think I've done something and there's like a little error message on the by, and it's something you can almost.
How does the done help?
The done just puts the error message at the end.
It will tell. Oh, that's great. I see.
You're saying at the end of the proof, you're saying I'm done, and you're saying no, you're not.
Okay.
And the error message just moves the error message.
Is it indentation important?
So the proof. So without, let me answer a couple ways. In general, indentation is important. So Lean is white space sensitive. And so it will distinguish between working on the first goal or working on the next one, depending on whether you're indented or not. So in general, indentation makes a difference. And sometimes you get funny error messages because something is indented that Lean thinks it shouldn't be or not. It's kind of this. Earlier versions of Lean had kind of begin end blocks. And in the move to Lean 4, Leo and the designers felt that instead of having begin and end blocks, sectioning things, it's nicer just have indentation to do it. And there are advantages and disadvantages, but I think now a lot of us have gotten used to it and kind of like it. As far as whether this kind of structuring using the dots and so on, you can get the proof to go through without using the dots. If you have a proof that works with the dots, you get rid of the dots, it should still work. It just helps. It makes the proofs more robust, easier to read, more maintainable. That you clearly demarcating the structure of the proof.
How do we know at this point that there's another case of induction? We do know that, but.
Yeah, so it's just the fact that, and so this is what I was saying yesterday, it's kind of an annoying, that we should have, at this point, we should be able to see the next goal, but you actually you don't see it until you go down to the done. I think, people have talked about it, I mean, this is a bug, and apparently it's not easy to fix, it's the syntactic.
It's not the done,
parsing.
it's an extra space. Wouldn't that, would that happen without the done?
Space worker, let's see, if we put a dot there, yeah, if you put another dot, you would see the next goal to be done, or, yeah, it's unfortunate that here it still thinks you're at the end of the previous line, somehow it hasn't. Yeah, I mean, parsing is a dark art in figuring out, where, okay. But, yeah, so, okay, but mathematically, again, you're not allowed to use any theorems about, congruence and powers. So if we want to prove this by induction, so mathematically, what would the strategy be? How would we prove?
Use the exponent rule.
Yeah, you want to expect a1 to the k plus 1 is, yeah. So there is a rewrite rule called pow_add, power, right? And it says a to the b plus c is equal to a to the b times a to the c. And if we do that, we'll get a1 to the k times a1 to the 1. And then there's another one that will rewrite a to the 1 to a. K plus 1, and adding 1 in the natural numbers is a special operation called the successor operation. And so there is a rule called pow_suck, which does what you want exactly in this case. And so I will rewrite with pow_suck. Okay. And it expanded the power on the left. Right. We want to do it again on the right, so let's do it again. And okay, and now. So now what we want to do?
So it's both the inductor, like how this is in the fact and the multiplication.
Yeah, so we want to use the rule that says that to show a times b is congruent to c times d, show a is congruent to c. And we did that before. This was this int mod int mol. So we could say, well, let's just do it like that. Apply int mod eq dot mol. Okay. And then this one is the inductive hypothesis. So we can say apply IH, and then A1 congruent to, that's just the assumption HA. And I mean, I think, just to show you that, if you just ask Lean what I should apply, apply question mark, ask me what should apply, it tells you right away, do int mod eq mol with IH and HA. So this is just a one-line version of exact is just like apply. It's very similar to apply, but it's used when the thing you're applying finishes off the goal exactly. And so it's it's kind of right. So we could say apply this thing and it would have the same effect, but it's kind of good form to when something finishes off the goal exactly. It's kind of good proofwriting form to signal that fact. So, but let me leave this. I'll post this file on Zulip when we're done. So let me leave it commented out so you have both versions. Yeah.
This is just syntax, but why is there square brackets for the rewrite and not for the apply?
Yeah, because rewrite, you're giving a list of things. So let's see, would rewrite syntax work if
you say apply, you can't say apply A, B, C, D.
Probably get, again, parsing, it's kind of a dark art and weird things. So I guess the comma in Lean 3 used to mean something else. And so if you did rewrite pow_suck, comma, something else, it would take rewrite pow_suck. Yeah. Whether with Lean 4 you could get away without the brackets, and whether, if you tried to eliminate the brackets from the syntax, maybe it would lead confusion to other things. Yeah, so I don't know. But the idea is this is kind of a list, and Lean will parse that as a list of expressions. The parser, that having the brackets says this is a list of things to
But
rewrite.
besides that, the thing, it's a list of I don't know what those are.
So this isn't, so here you're not
to
giving a list of things. You're not saying use this and then that. You're saying use the compound proof that you get by composing int mod eq mol with IH and H.
So we just understand like the int mod eq mol, that's a, what would you call that, theorem? That single object is a,
so
as opposed to the pow_suck or something else?
I can say have code equal So this is int mod dot modi dot mul IHHA is an expression, and the type of this expression, well, so the type of this expression is it's a proof of the proposition that of exactly the proposition in the goal. So you're saying take the inductive hypothesis, take the HA, and then compose them into a proof by adding that rule.
But what is PAL-SUCK? That's something different, an object of a different type?
PAL-SUCK is also a theorem. It's the for all
No,
A and
specifically,
K.
but it's an object, is it the same type?
Oh, so in this case, it's the identifier, but the identifier names the theorem, and the theorem is a proposition.
Oh, so they're all the
But
same.
now you're saying instantiate the universal quantifiers to get an equation, and then apply the substitution rule. So you're giving it the same kind of data, but in a different way. Yeah. Okay. So yeah, we're having fun. Let's keep going. So the last thing I want to do is just a couple of how to deal with logical operations like for all and exist. So here in the next chapter in mathematics and lean, there are a few exercises that have to do with logical connectives and quantifiers. So this is one of them. So here I'm defining the property. So if f is a function from reals to reals and a is a real number, I'm saying what it means for f to be bounded by a. So a is an upper bound for f, or f is upper bounded by a. And it's just defined to mean that for every x, f of x is less than or equal to a. And just from the logical form, the fact that there's a universal quantifier in front of that, tells us as logicians, looking at the logical form, that if you want to prove a statement of this form, right, if you want to show that something is upper bounded by a, you let x be arbitrary, and you reason about, you show that arbitrary x has the property that f of x is less than or equal to a. On the other hand, that if you have as a hypothesis that f is upper bounded by a, then you can instantiate that hypothesis to anything. Instantiate it. You know that f of 5 is less than or equal to a, f of z squared plus 7 is less than or equal to a. So mathematically, this is just kind of trivial. You know how to prove a universal statement by then taking an arbitrary one. You know how to instantiate it. You know that you can instantiate it. What the next chapter in mathematics and lean does is it just shows you the syntax. It just shows you the commands that it's part of taking the things that you know in your bones how to do and just telling you how to type it into the computer. Okay. So the way you prove a universal statement is by letting x be arbitrary. Is you use the intro tactic. Right. So for example, here the next theorem, the example we want to prove is that if a is an upper bound to f and b is an upper bound to g, then a plus b is an upper bound to f plus g. So lean knows that f plus g, so that is syntax for pointwise addition. So it's the function which maps any x to.
I'm sorry to ask all these questions.
Yeah.
What's the difference between def, fun, ub? That's a def. That's not. You wouldn't call that a theorem? I mean.
Yeah, because this is defining a predicate. It's defining what it means, right? And so if we check, f and ub, right? It's a proposition. Depending, given f and a, right? It's just the statement that I haven't proved anything. It's just the statement that a is.
I see. It's just the. Now
Yeah.
I saw that.
Okay. But now to prove this theorem, I'm actually going to construct a proof from the hypotheses that a statement of that form is. Okay. And so I guess another thing to know to lean is that often if you give it something that forces it to unfold a definition, it will. So, f and ub, f plus g, a plus b, is by definition for all x, f plus g of x is less than or equal to a plus b. And if you just kind of imagine that being a for all right there, you could give lean, you could say, intro x, let x be arbitrary. And so when you give that to lean, when you say intro x, lean will unfold the definition to see the universal quantifier and just perform the operation. Okay, so x is arbitrary. So f plus g applied to x should be, the same as f of x plus g of x. And pretty much you can treat it the same. If you want to lean actually to do the rewrite, there is a command called dsim, which is good for things like that. The D stands for definitional. You're basically telling lean unfold definitions and simplify, simplify by rules that are really just equations that unfold definitions. And so lean will kind of simplify things and show you that f plus g of x is really f of x plus gx. Okay. But okay, mathematically, what is the argument? We know that f is upper bounded by a, g is upper bounded by b. Well, we want that fx plus gx is upper bounded by a plus b. Well, I mean, again, this is kind of frustrating because what more is there to say, right? But we want a theorem that says that to show a x plus y is less than or equal to u plus v, it suffices to show that x is less than or equal to u and y is less than or equal to v. And there's a theorem that does that in the library in great generality in any structure where it holds. And so again, I'm going to ask you to guess the name. But the hint is that the theorems we try to name theorems so that if you just kind of look at the statement and you just say what you see, then you're getting. So the goal is to show that something plus something is less than or equal to something
A
plus
less
something.
than B.
You don't want to say A and B because you don't know how the theorem is proved. So okay, so erase all that.
Something like add, yeah.
Yeah, add. So if you erase all the concrete things, there's a plus, there's a less than or equal to a plus. Plus in lean is add. Less than or equal to is LE. So the theorem should be called, we should be able to apply add, LE, add. Okay. And there we have it. So f of x is.
So did self unfold like before you did that line, the hypotheses weren't written as less than or equal to, it was just written as that predicate.
Yeah, so I haven't touched the hypotheses yet. So add LE add.
Oh,
It's just so you're always looking at the goal
backwards.
and working backwards.
Okay. So we still have two goals after that.
We still have two goals
Okay.
after that, exactly. We're not done. But now this is actually going to exactly get to your question. So how do you show f of x is less than or equal to a?
Sorry, can I end for a second?
Yeah.
The intro X, what's it introducing it for? How does it,
So it's the rule that says to prove for all x something, you can pick an arbitrary x and reason about it.
so it matches which thing?
Because if you unfold the definition of let's do that. So let's do this. Let's rewrite. Let's manually unfold the definition. If you unfold the definition of FNUB, the conclusion really is that for all x in real numbers, f plus g is x is less than or equal to a plus b. And when you say intro x, lean looks at the conclusion and says, I don't see a universal quantifier. There's a problem here. But that pushes it. It says, okay, let me try to fix that by unfolding that.
So rule one is about the conclusion that you're introducing.
Yes, so most tactics, there are tactics that act on hypotheses, but most tactics you're looking at the goal and doing something to the goal. So as Melanie points out, now there are the two hypotheses you have to prove. So f of x is less than or equal to a. Well, HFA says that for every x, and you could have called let's even just call x y, right? Right. I mean, you can pick any variable, right? But we know that everything f of anything is less than or equal to a. So anyone want to guess at? So now, I mean, that this follows from HFA, from the hypothesis. The only question is, what's the damn syntax that lean expects you? What's the magical incantation that you have to write? And the hint is that you already know it, because we've been doing it all along. In fact, we just did it. So if I want to use HFA to prove the goal, it's just apply. You just want to apply by apply. That's exactly what apply does. It matches the conclusion, and it says, oh, well, I have a for all, I have to instantiate that, the x, for all x, I have to instantiate that to y. But that's exactly what You know, I mean, we just did the exact same thing with add add is the theorem that for every A, B, C, and D, right? And it just kind of, it matched it to the A, B, C, and D, you know, and then just apply the rule. Okay, so we say apply HFA, then apply HFB, sorry, HGB, right? And then we're done. Okay. Yeah, let me mention that what you're really doing is when you do these applies, you're kind of building this compound expression. And the compound expression that, in this case, that you built is exactly H. Oh, I think it's complaining about, no? Oh, sorry. HFA, yeah, applied to X, applied to Y. Sorry. This is exactly the compound expression that is built. You've taken HFY and applied it to Y, then you've taken HGB and applied it to Y, and then you did the compound expression add Eliad.
So it would be right to say that that's the forward chaining argument where you start.
This is what's called the proof term. This is writing the proof just as an expression.
Right.
And yeah, so I'm trying to point out, although not doing it well, is what a tactic 2 proof is doing is constructing the expression just piece by piece.
And it's usually going backwards, right?
And it's usually going backwards. So the add Eliad, you know, adds the first thing and kind of then leaves you the goals to figure out the 2 arguments.
And here you're
And then
going
you
kind of
could,
forward, you're saying, here's a hypothesis, let's combine them and then let's.
yeah,
apply
you're
it.
just kind of doing it in
Yeah,
one shot.
Yeah.
And yeah, and another thing to point out is that, again, if you just ask me, you know, what is it? It tells you that it's, it'll give you that. Oh, and the other thing, right, to point out is, you know, when you do it manually, you know, if you're curious to see what it is you've done, there was this nifty proof term tactic that I showed you yesterday. You could say, you know, what is, no, show proof. There's a, no, and then wait, what was it? What was it? I had it up there. Show term. Take the average of the, you're showing the proof term, right? So show term. Show the expression, you know, show the thing that the tactic proof constructed. And it shows you that, you know, that's exactly what those commands built. Okay. So that's typically the universal quantifier. You know, to prove a universal quantifier, you're going to use intro. To apply it, you just apply it. Again, there are lots of variations that are discussed in mathematics and mean. But let's move on to the existential quantifier. So here I'm asking you to prove that there's a real number between 2 and 3. If I ask everybody what's their favorite number between 2 and 3, I mean, you'll say E or something like that. But let's use 2.5. Right? But the command, you know, to prove that there exists something with blah blah blah. I mean, again, there are lots of ways to do it. Sometimes non-constructive, using out. But the most explicit way to prove that something exists is just to name it. Right? So just tell me what the thing is between 2 and 3 you want. And the tactic that does that is called use. Just say, you know, use. So I mean, what I'm going to do now is say use 2.5, or you can use 5/2. So either one of these will work. I think. I hope. Yeah. So that's what use does. So if you're trying to prove an existential quantifier, the most straightforward way to do it is to just name the thing that is going to do it, and then you're left with the goal of showing that, you know, 5/2 has that property. And now I can show you the rules for and, but let me show you that there is something when you're just calculational, a good thing to try is norm num. I think simp will also do it. No, simp didn't do it. There's a tactic called norm num which does calculations, and again, you can read about it in mathematics. And mean, here's the short proof. Okay. There's a more interesting question of if you have a hypothesis that says that something exists, how do you use it? And again, mathematically, we know how that works, right? If you know that there is, f is upper bounded by a, you just say let a be an upper bound for f, and you start reasoning about it. So there is a straightforward mathematical rule. We know something exists, reason about it. And then the only question is, what's the magical incantation that you use? And so I'll show you that as well. But it's just, again, what I'm trying to convey is that I'm just giving you the syntax that that encodes the steps that you would naturally take. Okay, so we're kind of upping our game a little bit. We're proving now. So now we have a predicate that says not that something concrete is an upper bound to f, but just f is bounded. Right? So there is an upper bound for f. So the predicate fn has an upper bound, has ub, applied to f, saying fn has ubf means exactly that. There is an a such that a is an upper bound to f. So now we're trying to prove the theorem that if f has an upper bound and g has an upper bound, then f plus g has an upper bound. And if we knew what the upper bound is, we would use the use tactic, right? Because the conclusion has the form, exists a c such that, for all x, f plus g of x is less than or equal to c. But, we don't have it yet because somehow the information is buried in the hypotheses. So what we want to do is we want to use the fact that f has an upper bound. We want to say, let a be an upper bound to f. Well, let's even use it different. Let's let u be an upper bound to f. And sorry to do this to you, but the magical incantation. There are a number of magical incantations that will do it, but the one in mathematics that we favor is to use a tactic called R cases. And the syntax is you give it the hypothesis that you want to split apart. And then you have to give it a pattern that tells it how to unpack all the information. So in this case, we want to get a u, and there should be a property of u that says that for all x, so there it is. After you apply the tactics, you have a u in the real numbers, and you have the property hu that u is an upper bound to f. So the way to think about this is we've unpacked the hypothesis that there is an upper bound to f, right? And we've given the name, we call in the upper bound u, and hu is the name of the fact that u is an upper bound to f. The angle brackets, you get them by doing \less than. So I'll remind you that you can see how to type Unicode symbols by hovering over them. This looks like kind of weighty syntax, right? Having to type the angle brackets for something that's really simple. R cases is really powerful. It's used to unpack lots and lots of kinds of information and can do a lot of it at once. So it's really powerful syntax. So we're using a canonical simple instance, but yeah, we did want to give you kind of like the general syntax first. So that's it. So UBF is the statement that there is an upper bound, and then after the width, you get the pattern that tells it how to name the things you're getting out of it. Okay, and so similarly, the fact that UBG, so let's call it V. Oh, and it's common to name hypotheses. I've just been doing it, so maybe you picked that up. But it's common to use, the letter H as a label to signify, that you've got an hypothesis. You can choose any name you want. You can say my favorite, hypothesis. And Lean will, happily use whatever syntax you give it. But just kind of mathlib conventions are to, this goes back to Koch and a lot of proof assistants to just use H for hypothesis, right? Because, data and hypotheses are kind of listed together. It's often useful to have mnemonics to keep track of what's what. Okay, so we have an upper bound U for F, an upper bound V for G. We want to get an upper bound for F plus G. So what's the magical upper bound? Yeah, and how do we tell Lean that we want to use U plus V as the upper bound? So you say use U plus V. Okay, and so now this should look familiar, right? We want to show that, so we have that F, U is upper bound for F. b is a upper bound to g, you want to show that u plus v is an upper bound to f plus g. Right? We just did that.
Do we name our thing?
Did we name it? Did we name it? Let's see. Yes, we did. We called it FNUB add. So what do we want to do here? We want to use, we're going to apply. So you just apply FNUB add, UB underscore add. Wait, what? No.
Lowercase.
FNUB, good, yeah. Yeah, this is, again, lean naming syntax. It's even when the predicate has an upper case, yeah, it's just lean syntax, you use lowercase in names of theorems. Let's see if things are set up, we should be able to just say HU, HB. Yeah, Emily says, no need to be sorry. Do they still show like love story to incoming freshmen here? You know, love means never having to say you're sorry. When I was a freshman at Harvard, you know, every freshman you would go in and watch it. Love story. It's a novel by it was a cheesy movie in the 70s. Yeah. So love means never having to say you're sorry. Lean means never having to say you're sorry. Okay. You've done for a while. Maybe one more.
Could you just,
Yeah.
what was the goal right before the apply, up there? One line up. Oh, yeah, there, no, that's fine, yes.
Yeah. And if you hover over what was the theorem that we proved, it was exactly that. If you have an upper bound for F and upper bound for G. Yeah. Okay. Let's do one more just to show you the disjunction, and then we'll call it a day. And I'd really rather have you play around. I guess I had this example here to show you that based on what you've seen, you can already prove non-trivial theorems. That, you can define what it means for a sequence. So saying that S is a sequence of real numbers in lean, we encode it by saying S is a function from the natural numbers to the reals. So it's a sequence S0, S1, S2. This predicate says that S converges to A, right? So for every epsilon greater than 0, there is an n such that for every n greater than or equal to n, the absolute value of Sn minus A is less than epsilon. So it's just the usual epsilon definition of convergence, right? And based on what you've seen, you can already prove things that, well, for example, the constant function, which maps anything to A, converges to A. But more interestingly, that if S converges to A and T converges to B, that S plus T converges to A plus, and in fact, yeah, we can even so again we can even use sort of the sequence to connect sequences just point-wise, and so already it's just gonna be intro and use and yeah, you're gonna need some rules to have the triangle inequality with that, but already you've seen enough pretty much to do some non-trivial mathematical theorems. Let me just show you one more logical connective, how to use OR. So the rules for using OR is if you want to prove P or Q, well, either you prove P or you prove Q. You can prove the disjunction by proving one or the other, which seems counterintuitive because if you could prove P or Q, then you wouldn't have stated a disjunction, right? You would have stated just P. Right, but typically, a disjunction will come from a hypothesis that has kind of a disjunctive character. Okay. So here's the theorem I want to show that for every x and y, if x is less than the absolute value of y, then either x is less than y or x is less than negative y. And again, it's a silly example, and it's certainly in the library. I mean, if you just ask. If you just ask lean for a theorem that does it, it's less than underscore abs dot MP. Tell you what the MP means, but it's it's a theorem about less than absolute value. But rather, so I want to use this to illustrate how you do proof by cases. So the facts that we're going to use is first of all that for every LE or greater than says that for any two numbers. U and B, either U is less than or equal to B or U is greater than B. So we know that either 0 is less than or equal to Y, then 0 is, or 0 is greater than Y, right? And then splitting on cases, if 0 is less than or equal to Y, we should be able to write the absolute value of Y, to Y. And if if y is less than 0, we should be able to write. So, so to do a proof by cases, there's a tactic that's called by cases. Sorry, no, it's not cases. Sorry, I want to do R cases. By cases does P or not P. So I want to do LE or greater than 0Y. And here the pattern is, instead of unpacking this to get, like an existential statement where there's, a quantity and a property, there are two possibilities. Let's call it H1 or H2. And so here our cases is doing a disjunctive split. And here I'm saying I want you to call the first case, H1 and the second one H2. Okay. And so now you see there are two goals. It's just a proof by cases. There's case 1, case 2.
Can you show the definition of LE or?
Yeah, so LE just says that either A is less than or equal to B or A is greater than B, right? And so now we can split on cases on that. So it's really just proof by cases, case 1, case 2. And the goals really are disjoint. So I could have used H1 for both, right? And in fact, I typically do that, right? So I can name the hypothesis H in both cases. Right. So in this case, cases did a disjunctive split, and now you have a proof by cases, case 1, case 2. And yeah, so let's just do the two cases. So in the first case, we want to rewrite the absolute value of y to y, right? And so in the first case, we want to rewrite, so we want to use abs of non-neg h. So the error message is that I'm not done, so let me put that there. So what I've done is I've done a rewrite to make x less than absolute value of y, x less than or equal to y. So now I'm trying to prove an implication. Intro also works for antecedents of an implication, right? So to prove x less than y implies whatever. I want to assume that x is less than y and use that fact. I can do that with throw h1. And now to prove the disjunction, we want to prove the left side of the disjunction. We want to prove that the OR holds by showing that the left. And so the left tactic says go left, and now we can say exact h1. Okay. In the other case, we want to use abs of neg h. And so we wrote the absolute value to negative y, which we can do because y is less than 0. And pretty much the same thing will work, except we want to use the right side of the disjunction. And that's the proof. So there are more interesting examples and exercises, in mathematics, but the point is, I should say that, with logical connectives, every connective essentially has this kind of dual use or dual interface. One question is, if you're trying to prove a statement with that connective, what do you do canonically? So if you're trying to prove a for all, you let x be arbitrary. If you're trying to prove A and B, you split into two parts and you prove A and you prove B. So this is called the introduction rule. There is also, conversely, if you have this connective in a hypothesis, how do you use it? Right. So if you have a for all, right, the way you use a for all is you apply it to something you instantiate. If you have as a hypothesis, P and Q, well, that means that you have P and you have Q. So there's kind of reasoning backwards from the conclusion, and those are called introduction rules. There's kind of reasoning forward or using hypotheses, and those are called elimination rules. And so what I'm showing you here is that, the elimination rule for an OR is to do a proof by cases. And, our cases is the magical syntax that does it. And the way to prove an OR canonically is just to prove the left or right side, and the left and right tactics are the syntax that will do that.
I have to confess the confusion here. The OR cases is qualifying the less than, equal, or greater than, or is it something about the hypothesis?
So the R cases is taking this whole expression,
Yeah,
which is a proof that either 0 is less than or equal to y, or 0 is
Right.
greater than y. And R cases says, I want to, so that's a fact, right? It knows that, that's true for every y, you have that. And now R cases says, okay, so using that fact, I want to prove my goal by considering each case separately. So I know that it's one or the other, right? At this point in the proof, I'm trying to prove this statement at the bottom, but you can prove it by splitting on cases.
I see, so
And
you split on the cases, and then within each case, you're now going back to the goal.
Yes, so now the goal has not changed, right? So this is kind of a reasoning forward from hypothesis type thing. The goal hasn't changed, but now in each case, you have an extra hypothesis. Okay, so this is a good place to stop and just let you have fun with mathematics with me, and I will, I'll hang out and answer questions.
I'll turn off the recording.